Welcome, everybody. It is great, seriously great to see everybody. To get started, let's just jump right into Kristen's program. Kristen's been a radio amateur for some time, a graduate of MIT, presently works for Apple. As far as we're concerned, one of her greatest recent contributions is that she's the ARRL's technical coordinator for our East Bay section and president of the Palo Alto Amateur Radio Association, amongst many, many other things. She's obviously a very busy woman. Most of us have heard her speak at Pacificon. I have since my first year in amateur radio 2 Pacificons ago, and where she baffled me and I had to go look up about every third word she said. Anyway, without further ado, please let me ask you all to welcome Kristen McIntyre.
Well, thank you. By the way, just a quick note, I'm also on the board of the ARRL. I'm Vice Director for the Pacific Division. And we are having a board meeting starting this Friday, so fun times. Okay, so we're going to talk about, I like to do these talks about amateur radio stuff that people kind of take as conventional wisdom or believe certain things about and just kind of mess with it a little bit. And this talk is one of those kinds of talks because I've done this before with a few other topics, but one of the things that comes up all the time, especially on the 9am TalkNet, which I'm the net control for on Fridays, is people ask about SWR. And a lot of times I end up just saying, who cares? So let's dive into this a little more and see what it is. So what do you think SWR is? Is it breakfast cereal? No, maybe not. Maybe it's a floor polish. I'm not thinking it's that. It could mean slower, S-L-O-W-E-R. It could be an obsessive compulsive disorder, which I really believe is true. So some people really think about it that way. And but we actually call it standing wave ratio, and we're going to dive into that a little bit in more detail to try and understand what standing wave ratio is all about. So I'm sure all of you know that guy. Somebody gets on the radio and they say, oh man, my dipole is now at 1.12 to 1. I have to tear everything down and figure out what's wrong. You've probably seen this person or talked to this person on the radio. Also, there's this common notion that resonance is 1-to-1 SWR. You probably heard that one too, right? But it may not be true. And the one you hear most often is that power is wasted. So if the SWR is not 1-to-1, you're throwing power on the floor. It's a myth, where I just say basically ground is not something that's a useful concept. This is not exactly like that. There are, of course, many misconceptions about standing wave ratio and what it means. And in this case, there's actually a clear definition, unlike ground, where there is no real clear definition of what ground is. And it's a valuable concept if it's properly applied. The problem often is that it's not properly applied. People kind of take it as gospel that it should be one way or the other, or it matters in one way or another, and that's not necessarily true. So SWR is not a myth, but it is one of these topics of confusion for a lot of amateur radio operators. So what we're going to do is we're going to dig a little deeper into this. And in order to dig deeper into this, we're going to have to understand some wave mechanics, which some of you might remember from physics class or not. And we're going to try to take it in a way that all of you can understand and see what standing wave ratio really looks like and see how we calculate it, which is not really a hard calculation. But the more important thing I want to convey to you is to show you what we're measuring. And then once we see what we're measuring, then we can look about what we should care about. So let's dive in. So wave mechanics, what is it? Well, we're studying wave propagation. Now this wave propagation is something like a disturbance in a field. It doesn't have to be an electromagnetic field. It could be any kind of field. It can be a mechanical oscillation or anything like that. It could be, quantum stuff, it could be gravity itself, as we've seen with the LIGO experiment. But what we're primarily concerned with is sinusoidal oscillations. Now, wave mechanics goes well beyond that to any arbitrary disturbance in a field. Well, since we're talking about ham radio here, we're going to be more concentrating on sinusoidal stuff. But I am going to talk about pulses and things. And I think that will help illustrate some of the points of how this wave mechanics works. So, wave motion. So, waves are typically thought of as sinusoids for us, and it's a simple harmonic motion. These are the governing equations you see on the right-hand side. The real version, in other words, without the imaginary component, is right there, you know, a sine omega t plus phi. Phi is the phase, omega is the radian frequency, which is 2 pi f, which is the frequency we're more used to. And of course, the speed of light is in there if we're going to have, you know, if we're going to talk about electromagnetics. The speed of light is very important because that's how fast things propagate. But at the bottom, you can see, and if you're an electrical engineer, you'll probably recognize that e to the minus j omega t, or j omega t plus phi, which is the phase. So the complex description is actually the more accurate and thorough description, but the real part works well enough for most stuff. Now, let's talk about mechanical waves. I think that in trying to understand this whole concept, mechanical waves make it easier to understand. There's things you can actually try at home. You can actually see stuff happening. With the electromagnetic version, you know, it's kind of hard to take a magnifying glass and look inside your coax. There's not much you can see there very easily. But with mechanical stuff, you can actually see it. And you know, we have in the electromagnetic case, we have electric fields and magnetic fields. But when it comes to mechanical stuff, we have tension and motion. And with a rope, we can kind of look at it that way. Have you ever just taken a rope and just flicked it and you see a wave propagating down? That's the same sort of thing here. And you can see the picture here is of what's called a Shive wave machine. Has anybody ever seen one of those? They're really cool devices. I can't buy one. I would love to buy one if I could find one of the appropriate size and price. They were originally developed at Bell Labs, and there was a very big one at MIT in 26100. If you've ever been there, that's a big lecture hall, the biggest lecture hall at MIT. And no one ever seemed to use it, which was kind of weird, but I really like them. They're really interesting. So let's look at traveling waves. Hopefully the animation is not going to be too stuttery coming over the connection here. In this case, we have a wave that seems to move across the screen, or it's moving across this graph here. And to get traveling waves, we have impedance matching. And yes, indeed, we can impedance match in mechanical systems as well as electrical systems. So if we have a proper impedance match, we have this traveling wave that seems to go from left to right in this particular graph. All the points are changing, and it's basically traveling because the peaks are moving down the medium. That's what we define as traveling waves. Another property of waves is called superposition. And many things in physics, when they're linear systems, have superposition properties. So we can have multiple sources of a wave, and they'll just kind of live on top of one another. And I'm going to start up a little animation here. You can see this. You can see two pulses that come together and they meet in the center, and they seem to just pass through each other. You see how the little one keeps going on the opposite side, and they add while they're on top of one another, but they remain independent. And this is a really interesting property. And what this leads us to see is a little bit about how we can get other waveforms that kind of look like not the original one. So if I start the other animation, you'll see two sinusoids, one of which is fixed in phase and the other one has a changing phase. And as the changing phase moves across the seemingly fixed one, the bottom is the summation of the two, or the superposition of the two. And you can see that it kind of seems to get bigger and smaller and not really move, or maybe move a little bit, but it's mostly just reversing phase and getting bigger and smaller. And what you're seeing is kind of a sort of like a a standing wave. It's almost like a standing wave. So the point here is to see that you get addition and subtraction. On the bottom one, when the peaks and the valleys all line up, you go to 0, and then it comes back. Now, a useful way to think about this, in my opinion, and this is the way I learned this stuff years ago, is to talk about boundary conditions. So what is a boundary condition? It's what's at the boundary between one medium and another. So if something's in a medium where it's continuing the same way, it'll just keep going until it hits some boundary, and at that boundary, things change. And this is a useful exercise for us here, because we want to look at what happens when we take a pulse and we send it down, say, a piece of rope, and we have, for example, one end of the rope free. Let's say we kind of have it against the wall and it's on some harness that allows that thing to move up and down freely. So we'll start that one here. You see it on the bottom. See, the pulse comes in and it goes to the free end, which is the wall there, and it moves, and then it kind of comes back. And what we're seeing here is that there's no tension at the end of that, just only motion. So this is kind of like an open circuit. So the energy moves down, it matches the deflection or at the end, and then just continues to come back. And if we instead hold the end of the rope steady, you'll see that we get a different effect. So if we don't let it move at the end, we have to obey that boundary condition where nothing moves, and we see it flip over. And this has to do with the momentum that goes into the wall and then comes back out again. And it actually flips the pulse over. And if you have a piece of rope and you can set this setup going, you can actually demonstrate this at home. And of course, this is an extreme example. So we have that something on the top that looks like a short circuit and something on the bottom that looks like an open circuit. And we get different effects. And if you recall, in a piece of coax, you get a very similar effect when you have it open versus shorted. Now, so what happens if it's somewhere in between? It's not held steady and it's not really loose either. We have a change in the medium, for example. So what are the boundary conditions? From the boundary conditions, we can actually look backwards and see what's going to happen. So in the top illustration, we see a pulse that's going to come in, and the rope gets thicker, which means that it's going to be constrained in its motion to be less motion than before. So we should see some amount of that pulse come back at us. And you'll see that some amount gets reversed, sort of like it's attached to the wall, but not really strongly attached because some of the energy continues to propagate down to the right. Now we have the opposite on the bottom, and we see a pulse go there, and we're going to see part of it come back in the same amplitude direction. So it's like it goes to a looser thing and comes back, and this is similar to not having it constrained at the wall. So you see pulses go down, and then they kind of separate and return. And these are reflections, and they're reflections because we have a mismatch in impedance, where impedance is the kind of the stiffness and deflection of that piece of rope. In all of these cases, we conserve energy and momentum, and those are basic principles of physics, and that's why we see this. So if we apply the constraint that energy and momentum must be conserved, this is what comes back. Now, standing waves happen whenever we have a mismatch. So in this case, we're not going to send pulses down. We're going to just send a sinusoid down, and at some point, we're going to reflect it back. And what we get is effectively things traveling down and then a certain waveform traveling back. And you can see when we do the addition and subtraction of the two waveforms, we get something that seems to be stationary. It's not really stationary. We're just getting stationary peaks and troughs. So if we look at the overall envelope, we'll see that that seems to be stationary. It's a stationary interference pattern between the two. But we call this standing waves because it appears to be stationary. It's not really stationary. It's the superposition, again, of this incident wave and then the reflected wave. And from that, we derive this thing called the standing wave ratio. It's the ratio of the peak to the trough of the envelope. not the actual instantaneous, although you can calculate it instantaneously, but in general, when we talk about it for something on a meter, it's the envelope peak to trough of the peak to trough ratio of the envelope of that resultant summation of the waves. And this, of course, applies to mechanical waves too. And it has a very clear definition right here. And you know, we have these Z and Z naught. Z naught is the characteristic impedance of the medium that is going through, which could be a piece of rope. And the Z is the impedance that it's hitting at the end. And we can calculate this thing called the reflection coefficient, gamma. And then from that, we can calculate the SWR. In this case, I put a V there for voltage, but it doesn't have to be voltage. It could be something else. Mm. Now, characteristic impedance is something that I kind of alluded to. Whenever you have a transmission medium, it has a characteristic impedance, and it's the ratio of a couple of parameters, sort of like resistances for voltage and current. We have this, in the case of a rope, we have deflection and tension. And in the mediums we've been talking about, this is roughly a constant thing. It's determined completely by the physical characteristics of the medium. And there's a little animation here that I stole off the internet, a piece of it. And it's going to illustrate what happens if you had an electrical medium to go through. That might be like a transmission line. And you can think of transmission lines as a series of inductors and capacitors. And so the energy goes in, charges up the fields in the inductor, charges up the magnetic field in the inductor, the electric field in the capacitor, and begins to propagate down. And it's delayed because, you know, it takes time to charge these things up and change the fields and slosh the energy. So you can see, I'll start the animation now. As it comes down and connects, and you'll see voltage is kind of this lifting thing, and then you can see the current going down in this animation. It's not entirely accurate, obviously, but you can see it's kind of transferring the energy from stage to stage to stage as it gets down towards the end. And at some point, it's going to encounter an open circuit here at the end, and you'll see that the open circuit doesn't have any place to put the energy, so it kind of flies up high. And then this is like that unconstrained rope propagates backwards. And so it's the same effect as we had with a mechanical piece of rope. And the characteristic impedance is what impedance would go on the end of that thing to take that energy forward. Now here's what a match would look like, and that's where we actually take all of that energy along that rope and we transfer it from stage to stage to stage, and then finally we either absorb it or transfer it to something else. And so in order to get that to actually happen, we have to match the impedance. And in this case, it's deflection and tension. And we're doing a certain amount of work. There's a very specific definition in physics of what work is. It's force times distance. Well, it's actually a vector quantity, but this, you'll see the force being transferred along this shive wave machine in a moment. And there's this thing called the work energy theorem, which says that work and energy are the same. So work is force times distance, and that represents energy that's moving around the system. So let me show you this. You can see the energy traveling along the wave machine here, and this wave machine is matched at the end. So what you'll see is it gets to the end and completely disappears. So that energy is being transferred into heat, for example, at the end of this thing. So all of the wave motion has disappeared towards the end, which is, I think, a very interesting demonstration of what a terminated transmission line is like. So we have basically this transmission line, which is a mechanical piece of machinery here. And at the very end, we terminated it with the right resistor so that nothing comes back. So I'll run that one more time so you can see it. You see the propagation there were two oscillations put into the system, and it travels to the end, and the energy and all the momentum gets transferred into something else, which in this case is like a dash pot that turns it into just heat. But you're probably saying about now, what the heck am I talking about this stuff for? This isn't really ham radio. I'm trying to take you back to high school physics or something. But really, it is. This is all about ham radio. In the case of the mechanical systems, the deflection is sort of equivalent to voltage, which is like the electric field. And the tension is kind of like current, which is the magnetic field component for the most part. And you've seen, as we moved along here, that some of the constraints were the same. We had the shorted one, the open one, and what happened to the energy was really interesting as it moved towards the end and then had some encounter with something that was different. And I wrote here that it's a great analogy, but it's more than an analogy, it's a real equivalence. So there's the same sorts of principles at work here. So it's not just, you know, like the water analogy of voltage and current, right? That's an analogy, but this is actually the same effect going on. So in COAX, we have the same kind of waves that we've been talking about before with the rope and all of the other stuff, except for we have some more dimensions to deal with. So inside the COAX, we have the E field and the H field, so electric and magnetic fields that are propagating their way down the coax as it moves, but it's the same sorts of principles. The electric and magnetic fields propagate between the conductors in that space between the center conductor and the outside conductor, and it has a characteristic impedance because the energy goes in and it kind of changes those electric and magnetic fields, and they move down the piece of wire at a finite speed, which is at generally less than the speed of light. As you may have noticed, if you have a piece of coax, things move a little bit slower. That's called the velocity factor, and that has to do with charging up these capacitors and inductors as it moves. Open feed line is still the same principle. We have, it's a little bit easier to think about because we can kind of see it on the outside a little better, but it has its own characteristic impedance that's defined by how close or far some conductors are and the interactions of the electric and magnetic fields in between those two conductors. And you know, if we want to see what's going on, we can actually put a light on the wire and capture a little bit of that energy and see where the peaks and the valleys are. Let's say we have standing waves going on there, we can actually see the standing waves with the light bulb. But it's the same effect, it's just a slightly different physical configuration. One of the ways that help us think about these things is this thing called the Smith chart. I'm sure all of you are mildly frightened at this point because you're seeing the Smith chart and you're going, oh God, no, she's going to talk about Smith charts. But I'm trying to make it a little bit easier for you because they're really useful charts. It's sort of like a circular slide rule for transmission lines. And it makes it really easy to estimate impedances. And there's a real thing I want to show you about this that will help you understand what SWR isn't. So SWR is just one input to this thing. It's completely independent of the system impedance. We're very used to 50 ohm systems, but if you had a 300 ohm system or a 75 ohm system or a 30 ohm system, this would all work just the same. We just scale it a little bit differently. And what this is, if you're into the math part of it, is a conformal map of gamma, which means this conformal map basically means that all the angles are preserved. So let's take a look how these things work. So right in the center of the Smith chart is this thing called prime center. That's where it says 1.0 right in the center. And that's our reference point for whatever system impedance we're going to look at. So if we have a 50 ohm system impedance, we're going to say that 1.0 is equivalent to 50 ohms and scale everything appropriately. We have things called resistance circles and reactance curves, and you can see those in those two representations right there. And then those are kind of overlaid on one another. So the resistance circles and the reactance curves are overlaid, and they represent impedances when you find a point there. So you can see that one point is pointed out, 0.5 plus J1, and that's of course scaled by whatever impedance, system impedance you're looking at. And you have a short circuit on the left and an open circuit on the right. All sounds very familiar in a sense. And rotation in this thing is distance, and distance from a generator or to a load. and it's all distance in wavelength. So it's a sort of a fraction of a wavelength, everything you come around. So the point here is that everything is normalized. Here's the complete chart. We have SWR circles here. Each circle represents the constant SWR. So the arrow there points out two of them. One of them is 2 to 1 SWR in that circle, and a 5 to 1 circle, just as an example. Now, how do you find SWR? Well, what we do is we scale to Z0. So Z0 is that characteristic impedance of the system. That's right at the center. So if 1.0, where the red dot is our characteristic impedance, we call that 50 ohms. And we plot, if we had some impedance, we could just plot it on here at the intersection of the reactance curves and the resistance circles. So we could just find, 30 plus J7 or something like that on there and just plot that. And then we make a circle centered at 1.0, centered at that prime center. And that's a SWR circle. And it has a radius. That radius is the reflection coefficient for that circle. And then where it intersects on the right-hand side, that is the SWR. So it's sort of, that's the real part of that on the real axis. And that actually tells you the SWR on there. So really convenient. You can just start with an impedance and say, let's say you measured an impedance at one end of a piece of coax, and you can say, well, my system impedance is 50 ohms. What is the SWR? You can calculate it right from this. You can also go in the opposite direction, where you can start with an SWR and try to find an impedance. So we plot some point on the real axis, which is the SWR. That's the right-hand side, right of the dot along the horizontal axis there. And only on the right-hand side for this. And we make a circle with that. And that SWR circle, again, that radius is the reflection coefficient. And then all along that circle are impedances that all represent SWR. So if you have an SWR of, I think this is about 2.5 to 1, I think, in this diagram, if I got it right. Kind of hard to see, it's very light, but I think it's 2.5 to 1, something like that. So for an impedance, of an SWR of 2.5 to 1, you'll note that all the points in the circle are the same SWR, all of them. And how many are there? There's an infinite number of points. So an infinite number of different impedances can lead you to the same SWR. But who cares? I mean, really. But it really does show you something really interesting. So the most important thing I want you to know is that an SWR is a degenerate measure. It tells you a little bit about the system, but it's one of an infinity of different states that the system could be in, an infinity of impedances. We also learned that the absolute system impedance is not important. It's the relative impedances of things in that system that make it what it is. So SWR will tell you something about energy transfer, but it won't tell you anything. And as the famous saying goes, a 50 ohm resistor has a 1-to-1 SWR in a 50 ohm system. Does that tell you how well it radiates? Not really. Other antennas may be also a 1-to-1 and have a different impedance, and it may or may not be useful to you. Now, so this is a way of looking at it. Here's the observations in detail. The absolute load doesn't matter, right? You have a 300 ohm system. As long as everything is designed around 300 ohms, we're good to go. The wave mechanics are all the same as we did in the mechanical cases. It's the same thing. And what we're trying to do with all of this is move energy from a generator to some dissipating load. And that energy propagates in a number of different ways. I listed 3 of them here, there's more. But for our purposes, the most interesting ways are it propagates as heat, it propagates in a mechanical fashion, or as propagating electromagnetic fields. So for now, let's just think about it that way. Now, what's a generator? I've talked about that a couple of times. Well, in ham radio circles, we call it a transmitter. But if we're looking at how wave mechanics works, we call it a generator. And here's a typical amateur radio generator. This is an FT100 that I ended up buying on eBay and fixing up and getting working again. You can think of that generator as having an equivalent circuit. And a lot of people think in a way that I think is incorrect and or unproductive about that circuit. But we'll talk about that a bit more in a minute. This transmitter or generator is usually designed around a certain impedance, system impedance. This is because it's a real world device, not a theoretical generator. So it has to be really happy driving that system impedance without getting too hot or breaking anything inside. Tubes or transistors, doesn't matter much. What it's trying to do is deliver power at the frequency of interest and deliver it to the load. So, and deliver it efficiently. Now, here's the thing that often comes up in these discussions, and I want to talk about it because it is highly abused. So many of you, and if I had you here in person, I'd be asking you to raise your hand if you've ever heard of the maximum power transfer theorem. And most of you who do dabble in electrical engineering or dabble in building circuits even have probably heard of this. So you want to impedance match, right? You've heard this with even audio stuff, impedance matching. So the maximum power transfer theorem says that if you want to have the maximum power transferred, you have to match the source impedance to the load impedance. Well, that's partially true, but it makes an assumption. The assumption is that the source impedance is a fixed value that you can't change. And what happens is people think that this applies universally, where it doesn't. It's not a symmetric theorem. It just says if the source impedance, and that's R sub S in this diagram, is a fixed value that you can't change, if you want to get maximum power out of the system, you match R sub L. And that is indeed true. But if you have an opportunity to change R sub S, you can make a big difference in this. So let's look at an example. I like to illustrate things like this with a degenerate case. So let's say that you have a 50 ohm RL. So that's your load resistance. And we can change our S. So let's go through an example here. Let's say that the source voltage is 50 volts. And it can be DC or AC. DC is fine. The RS is, now you're going to choose 50 ohms, right? You're going to say maximum power transfer theorem says they should be exactly the same. So the load is 50, so I'm going to make the source 50. Calculate that out. Power is V squared over R. Do the algebra or plug the numbers in, and you get 12.5 watts at the load. Well, that's some amount of power, right? But what happens if I choose RS differently? What happens if I choose it to be 0 ohms? Well, if I choose RS to be 0 ohms, and then I do the same calculation, V squared over R, I get 50 watts into the load. 12.5, 50, which is more? Well, 50, obviously. So I can get maximum power transferred when the source resistance is 0. And this, I think, is the point that's lost on a lot of people when they talk about the maximum power transfer theorem. If RS was set at 50 and I couldn't do anything about it, sure enough, RL should be 50 to get maximum power out. But if I have an opportunity to change RS, the source resistance, I'm going to change it to 0. Then I can get as much power out as is possible. Okay, so that's one of those things that, you know, when we talk about SWR, gets kind of muddled into the whole mess. Now, what's the source impedance of your transmitter? Well, it's not entirely clear. Many people think there's a 50 ohm resistor in there somewhere for a 50 ohm transmitter, but there isn't one. If you take any schematic and take a look at it, you won't be able to find the 50 ohm resistor. It's just not there. The transmitter looks a bit more like a voltage source, which means it's kind of, the source impedance is kind of 0-ish. But what we do is we design the circuit so that if it sees a 50 ohm resistive load, it's pretty happy to operate there. It likes it at 50 ohms. So it's matched so that it drives at 50 ohms and doesn't get hot and doesn't blow up the transistors. But the source impedance itself is extremely complicated and changes even through the cycle. So it's a bit of a complex thing, but it's not 50 ohms, for example. So what we're really interested in is what the transmitter wants to see. It wants to see a desirable impedance, something it can drive and be happy, something you can drive and the tubes don't get cherry red, the inductors don't get really hot, something like that. The grids don't start melting. We want to keep those finals linear, so we want it to operate in a linear fashion because we don't want any spurious emissions. That's a bad thing, obviously. And we want it to be efficient. And for us in the transistorized world, it's 50 ohms. In the tube world, it might or might not be 50 ohms. It could be something much higher. And originally it was designed around, around 300-ish ohms. So we're trying here to keep this transmitter happy. And it has a design specifications or where it's happy. If you've ever noticed, if you have a tube amplifier, and I love tube amplifiers, I have 3 of them, they can match a wide range of impedances. So they're happy at 50 ohms, they're happy at 100 ohms. When you tune that load circuit, that's what you're doing, is impedance coupling that in such that it's happy. Now, of course, we have real world transmission lines to deal with. So we talked about the generator. Now we're going to push some energy into a transmission line. But these transmission lines are not perfect. They have their own sets of losses. They have resistive losses, which is turning energy into heat. They have dielectric losses, which is a different way of turning energy into heat. We have, pieces of foam or stuff, dielectrics in there, and we have these little dipoles, and they're flipping back and forth. And those dipoles can generate a little heat too, because they excite the atoms in the dielectric. And we have leakage loss. So we have a little bit of energy that may escape out of the confines of a piece of transmission line. If it's coaxial, it's harder for it to escape, but it can. In the case of a balanced pair of lines, you can have all sorts of leakage by unbalancing those things. And in this real transmission line, we can have high standing wave ratio, which means we have a lot of energy sloshing back and forth in this piece of wire. And that can mean higher voltages and higher currents than you're used to, or that the wire was designed for, and that can mean more loss. So we have a lot more fields moving around. The wires can get hot, and that's generally what happens more often than not. There's certain circumstances under which you can get more leakage loss, but mostly it's some form of heat that happens when we have a higher standing wave ratio, and that's because we have higher voltage and higher current in different sections of the transmission line because of those standing waves. Now, if we look at the loss in coax, there's models we can use. Coax usually has a significantly higher loss, both statically and, by more statically, I mean a matched loss, and higher loss for a given amount of SWR that's not one-to-one over distance. So different coax types, different open line feeders, depends a lot on the dimensions and the materials that the thing is made of. The ARRL has a nice matched loss model that works pretty well, and you can find calculations for this online. And what you do is you say, well, what's the loss of the coax when it's perfectly matched? And from that, you can, let's say it's 1 dB, and from that you can derive the mismatched loss. And this is the equation you see on the screen here, but you can find that also in your amateur radio handbook. Just look for the matched loss model. And then you can calculate roughly, it won't be totally correct, what the actual loss is going to be at a different SWR. And to give you an idea of what that looks like, here's an example. This is a curve that I stole from a QST article. And so if you have some coax, for example, and in a matched case, for whatever length, it has a 1 dB matched loss. So you have a perfect match of your 50 ohm system into a 50 ohm load. And let's say it loses 1 dB over some run, whatever the run may be. And if you then crank the SWR up to 2-to-1 by mismatching it, for example, you'll notice that you get 0.2 dB of additional loss. At 5 to 1, you get 1 dB of additional loss, and at 10 to 1, you get 2.2 dB of additional loss. And you can kind of plot the points on the chart here. It's pretty easy. You have the additional losses on the vertical axis, the matched losses on the horizontal axis. So I took these numbers basically by reading them right off the chart here at different SWR values. And you just find out where that red line intersects the points on the horizontal axis, and that gives you the additional loss. And you can see, you know, it's not too bad for a 1 dB match loss at 10 to 1, which is a pretty bad SWR. I'm getting only 2.2 dB of additional loss, which is not that bad. You know, it's, of course, you'd prefer not to have that, but in some circumstances, it may be worth the loss. Mm-hmm. Now, if we have the transmitter and the load, we try to match the transmitter and the load to make the transmitter happy, right? We want the transmitter to be happy with whatever it's driving. We have choices about where we're going to create that match. And we can try to improve the match or make the match actually happen in the first place near the transmitter, which is mostly convenient. However, we get loss in the feed line because we changed that standing wave ratio in the feed line. We can move that matching out to the antenna, so we have a matched piece of transmission line all the way out to the impedance transformation, and that's really efficient because we're mostly not running at a high standing wave ratio in the coax, but that can be a real pain to pull off because you have to have a matching network remotely that will that's controllable and maybe needs power and some other things, and has to handle the weather as well. So what's that matching network look like? Well, you know them as antenna tuners. They're actually, you know, a kind of a matching network, a conjugate matching network. It's trying to null out this reactance and incorrect impedance to make it be what the transmitter would like to see. And you can transform the resistance as well as the reactance to get it to a point where it goes into the antenna and couples in some reasonable way that doesn't have too much loss. And the networks themselves have losses. Things like this one here that you see an example of has a lot of air gap components, which is very efficient. So capacitors that don't have that have an air dielectric, and then it's not that they don't have a dielectric, they have an air gap dielectric, are very efficient because we have very low dielectric losses. And if we have an inductor that just uses free space, doesn't have a piece of ferrite in it, it's very efficient as well. Ferrites have their own losses. Now, what about the antenna? Well, almost all antennas that we deal with are not characteristically 50 ohms. They may seem to be 50 ohms, and that may be for a number of reasons. But if we take a look at a free space dipole, that's 72 ohms. Our free space, the perfectly efficient monopole, would be 36 ohms. Yagis are often in the kind of 5 to 15 ohm range. And this doesn't mean that they're inefficient antennas. It just means that they have a different feed point impedance. And if you mess around with this feed point impedance, you can make some changes in it. And you can get different patterns out of the antenna if you do things slightly differently around this. But if you have an antenna and it actually, like, let's say you have a dipole and it's matching at 50 ohms, then there's probably something a little lossy going on there. It shouldn't actually be 50 ohms. It could be changed by the position of the elements, in which case it's not loss, or it could be near a tree, in which case it might be loss, all sorts of things going on. But if it's 50 ohms, you should be a little suspicious. And this happens especially with monopoles with ground radials. The ground radials will put in just enough resistance to raise that 36 ohms to 50. And you see this all the time. You know, if you've ever bought like a field vertical with a loading coil, the loading coil lowers that drive point impedance really a lot down into the 20 ohms, 10 ohms, 15 ohm range. And then they give you some really crappy radials, and the crappy radials end up heating the dirt quite a bit. And that causes it to match into 50 ohms pretty well. But that doesn't mean the antenna is efficient. If you get an antenna like that and you put down lots of radials, you'll find it doesn't match very well anymore, and you have to play around with it to get it to match, in which case a matching network may be the thing you need there. So when you have an antenna that shouldn't theoretically be 50 ohms and it is matching to 50 ohms, there's something going on there. So if we kind of recap here, what do we care about? The things we really care about in all of this is making the transmitter happy. That's the key thing. And if the transmitter's happy, it's going to couple the most energy out of your power supply and into whatever load you have down the piece of wire. We do care a bit about matching efficiency, and that's because we can make the coax get hot under certain circumstances. We can make it be even hotter under other circumstances. We can even make it arc, which is not a desirable outcome. But what we're trying to do is get to matching efficiency. If you account for the loss in the feed line, you may find that if it's a short run, you know, I talk to people all the time and they say, well, I have like a 5-to-1 impedance, 5-to-1 SWR. Should I put my tuner out in the yard? And I say, well, how long is the run? If it's 150 feet, yeah, maybe so. If it's, you know, 30 feet, who cares? It's probably nothing. It's probably so minimal that you don't care about it. So you have to balance all of these things against what your goals are and what losses you're willing to take, because ultimately nothing is perfect, and no station needs to be really perfect unless you're trying to do moon bounce. But the most key thing with all of this is to just get on the air and have some fun and not stress about it so much. If you want to learn more about all this stuff, here's some resources for you. Of course, the ARRL handbook has a lot of writings about this, and as well as the antenna book in more detail. There's a number of Wikipedia articles about standing wave ratio and wave mechanics. They're often kind of terse and sparse and very math heavy. So if you're into that, that would be a place to start. There are physics texts that you can get. You know, usually that's in the second semester of undergraduate physics. If you can find a book like that, you'll find more information about wave mechanics and that kind of thing. So with that, I'll take questions.
Thank you, Kristen.
Yeah.
Good presentation.
Kristen,
Sure.
This is now, I think, the fourth presentation I've heard from you over the years. And I have to say that if I may, and correct me if I'm wrong, your greatest observation at the end of all of these things is just to go out and do it, throw something in the air, get on the air, and not worry terribly about grounding or not worry terribly about antenna matching. Is that pretty much the high point of?
Yeah, that's the high point of all this stuff. It's like, yeah, don't obsess about it. You know, there's this perfection point out there that you probably will never achieve with your station. And you can kind of approach it asymptotically, but in order to have fun on ham radio, all you have to really do is get something in the air and talk to some people. That's the whole goal. And the obsessing part, you might as well just give up on.
Great, perfect. Well, I'm glad I've been getting your message. It's really refreshing to hear.
So Kristen, I'm going to open up a can of worms here. Can you hear me okay?
Yep, I can hear you. Go ahead.
I had all kinds of challenges getting a microphone to work. So in-fed half waves and 3-to-1 SWR from 3 megahertz to 30 megahertz.
Okay.
How do they do that?
So typically when you have that kind of a situation, there are losses. And this is how there are some antennas that are designed for the military, such that they can run, you know, from DC to daylight sort of, and still match the transmitter. And if you open up their little matching networks, guess what you find inside? Resistors. Because resistors, like a 50 ohm non-inductive resistor, will match perfectly from DC to daylight. And so when you have something that matches over a very wide range like that, it usually means that the Q is very low. And that typically means that energy is being dissipated as heat somewhere in the system. in a non-frequency dependent way, because there should be, if it's an efficient system, a frequency dependent component. Remember that wire is a transmission line of sorts, and it has a length, and that length matches the wavelength of some input signal. And if it's not moving with that different frequencies that you apply, something is lossy.
You know, and the nice thing is you see SWR plots on these, and they managed to design these things so you have nice dips on many of the ham bands, and you can't argue with the fact that they work. There's an awful lot of people using that antenna, making a lot of contacts with it.
Yeah, well, dips are different than flatness. So I was talking about the flatness case.
Yes.
But if you have dips, that's a different situation, where it may be loss, or it may actually be the way that the fields are coupling. Because if you have different length radials or different length elements here and there, you can get dips all over the place. Now, whether that corresponds to a good pattern or not is yet a second discussion to have.
Yeah.
Thank you, Kristen, for not calling the matching network an antenna tuner.
Yeah, that's a big bugaboo, right? It's not tuning the antenna, it's a matching.
Kristen, when the wave gets to the end, you showed an open. What should we expect to see if it's 50 ohms? How does it come back? In phase?
Nothing will come back if it's the 50 ohm transmission line. So if you match the characteristic impedance of the transmission line, that means that all of the energy is transferred in a perfect situation, of course. So you have energy that's stored in the electric and magnetic fields separately, kind of out of phase from one another. And that moves down the transmission line. And then when it sees like a 50 ohm resistor, for example, that energy is perfectly transferred into the resistor and turned into heat. So nothing will come back.
Thank you.
So, Kristen, this was an excellent presentation. I'm glad you did it on SWR. We have weekly nets and antennas and matching antennas, and getting them to radiate is a very typical topic that we discuss.
Well, I'm glad this was useful in some way, and maybe it can help kind of clarify your thoughts about it. That's what the object of the talk is.
All right. Well, again, on behalf of the club, thank you so much for coming. And I guess we're all getting used to this Zoom thing now. It's going to be the way of the world for a while. So.
Yeah, well, I hope next time I can see y'all in person. That would be even more fun.
Yes. That would be awesome. So.
I've got a comment that I was fascinated by your talk. I'm a relatively new ham, although I've been in radio and television and broadcasting most of my life. I never had to deal with these issues, but I've been finding that putting up antennas is a lot of luck and a lot of perseverance. And JB is a great teacher, and both Dick and JB and Art here all have been very helpful with me, and I seem to have working antennas.
I mean, you know, that's the other thing. The thing about non-perfection is, you know, throw a wire up. If you can talk to people, you're doing okay. Now, of course, there's the whole problem of anecdotal evidence, but and some things we know work better than others. I have another talk that talks about kind of what's important, and you know, it's called A Wire in the Air, what matters most, and that tells you a little bit about what in your antenna would be most important, and what you can kind of ignore, and that helps you put up compromised antennas and know what you're trading off.
I hope you can come back and give us that talk someday.
Sure, anytime.
Yes, yes.
Yes.
Yes, please.